Recording in progress.
So I'm sorry about the stuff that we missed. What we were just talking about, let's see, what were we talking about? Can computers compute anything? This is a problem that mathematicians posed and was answered by Alan Turing, which we're going to sort of come up against in a second here. So why I'm showing you this is that down the bottom, we have a lot of notes that are associated with each of these slides. And those notes I have reproduced for you and put onto D2L so that you won't miss them. And that's what these things are here. These are the notes there, right? So we can see there that programming, yeah, it can make you, it seems like your superpowers, but your superpowers are just that you can do stuff really quickly, mostly. Are there problems that computers cannot solve? Well, apparently. So this is the problem that was put by a mathematician in 1928. All right, so this video actually tells that story. So if you just take that link and have a look at it. Now, as I said, all that stuff's on D2L, so you can find it. But Alan Turing tried to answer the problem and basically come up with the idea of if you had two computer programs, one which would test to see if it was running or stopping. The other one that every time that the first program was running, it would stop. And every time that this first program stopped, it would run. And then if the second program called itself, then you could get a situation where you'd have a program which would never stop. And so, yeah, that's interesting. Sorry, that would be a problem that could never be solved. So computers, there are possible problems that cannot be solved. And one of those is the halting problem. Now, there's other problems which we are working on with computers that haven't sort of got the answers yet, and they have to do with prime numbers, composite numbers being, multiplying prime numbers together. They use this as actually a way of getting a special number, which they'll call a key, which they'll use for encryption in cryptography. So cryptography is so that you can take a message and put it into a scrambled form that other people can't read. And so if nobody can read it, well, how useful is that? Well, then you have a key, and using the key, you can unscramble it so it can be read. Now, the key is going to be a special number, and it'll be a special number which will be some calculation based on a prime number. Now, so you can use computers to produce a very large one, and you can keep that one. And if it's very, very hard to compute it, then you don't have to worry about hackers breaking your code. And so basically, that's what they've done with that. That's that. And that's mentioned here with the Rsa Factoring challenge, which the idea is to find large enough numbers that the computation of them, large enough prime numbers, the computation of them would be so big that it wouldn't be worth people's trouble, right? They wouldn't have, to take the time to calculate that number so that they could crack your code. Another problem, which seems to have not been solved by a computer yet, and actually this is an interesting problem because it gives us the fact that sometimes we just approximate an answer. We get an answer, we just say, oh, that's good enough, we'll just do that. And that was a traveling salesman problem. Traveling salesman problem being that, see, as you see, these things aren't in the notes there. They're only here. So it's a good thing I'm putting that there. The traveling salesman problem being that imagine a salesman goes from town to town to town to town to town. And those towns are sort of all connected by a bunch of roads, network of roads. And the traveling salesman has the thing that they want to do is they want to visit all the towns, but they don't want to waste too much time by going to towns more than once. So could we set out to go to every one of those towns without visiting any one of those towns once? That's a nice problem. And of course, mostly if you have enough towns and they're all connected to each other, you're going to get a situation where it's not really possible to not go through a town twice. But you could sort of approximate it. So there's a problem that tends to be hard, as it says, it's a NP hard problem. We refer to it as combinatorial optimization, but hasn't been solved yet. So we got some problems which are a little bit too hard for computers to solve. I guess we can leave it at that. So this one, all right, I don't know if you guys are, you wouldn't have seen this, but there's a set of cartoons that started in the 1980s, and I guess they're still going, but maybe not, but they were called Dilbert Cartoons. And the Dilbert Cartoons were supposed to show people in a business environment and sort of making fun of things that happen in a business environment. And a lot of those people were IT people. So, because a lot of IT people work in business. And so this is the problem of the, when you want to make a computer program, first you need to get the system requirements from the person who asked you to make the system. And this is making fun of the fact that people often don't actually know exactly what they want in the computer program that they want you to write. And therefore, they can't give you a proper specification. It's been like that for a long time. What'll often happen, especially if you're doing sort of rapid development programs, is people will say, "Oh, can you build this for me?" And then you say, "Okay, so I'll give you a first sort of blush of it, right? So we'll put something together in a week or two." And you show them that, and they say, "Oh, could you make it like this? Could you make it like that?" So what ends up happening is they end up with something quite different than what they thought about first, because as they saw what was possible, they realized that they wanted something else. So yeah, there's physical, practical limits. So our computers are limited. They're limited in their speed. They're not infinite. And there's, we have a limited amount of memory, limited amount of electricity, etc. Actually, so one of the computer programs that's sort of related to this, but not quite, is your sort of cryptocurrencies. Cryptocurrencies, they work on a thing called a blockchain. And so the thing is, the blockchain, what you have to do is you have to record all the transactions with Bitcoin. Actually, Ethereum is trying to do something a little bit different, but you have to record all the transactions back in a chain, and it takes a lot of computer power, to the point where actually the Chinese government forced people who are doing what they call crypto mining. So the idea of crypto mining is you'll do a lot of these mathematical calculations and find all the blockchain back until you get one which is unique. Nobody's ever calculated this one before, and then that's yours. And you can say, okay, I can sell that, and it's worth a lot of money. I mean, Bitcoin, it dropped in price by about 40% in the last couple of weeks, but it was at $60,000 for one Bitcoin. I mean, the first Bitcoins that were actually created, so this is not that long ago. I mean, it's like 10, 15 years ago. The first Bitcoins, guy used one to buy a pizza. Yeah, he used a Bitcoin to buy a pizza. And now they're worth like $60,000. I mean, how many pizzas you can feed a town on pizzas now from a Bitcoin. Anyway, so Bitcoin's there. The idea of that, I won't go into that. If you're interested in those things, go and do the degree in crypto, in computer security and crypto, because cryptocurrency, the idea is that we built a lot of security into it. Sorry, you were asking me a question about that. Sorry, when he buy pizza? It was one of the first with a Bitcoin, yeah. So when you bought, it's worth $1 or something. I don't know. When they first had it, nobody knew what they were worth. So I mean, it's just when they got the idea up. Now they're worth, like, as I say, now they were worth $60,000 a few months ago. I think it's like 40,000 now. So I mean, if you bought one at $60,000, you wouldn't be feeling too happy right now, right? I mean, I think, as I said, the Chinese government kind of made it illegal. They're saying no, and part of the reason why they made it illegal is because they want to make their own cryptocurrency, which is going to be different than Bitcoin and Ethereum and all the others. And it's just Chinese, and make all the Chinese people, if they do anything, they have to use their Chinese cryptocurrency. But the other thing is, it was just using so much electricity. So you had these people doing the mining, and they were basically using as much electricity as like a little town. They just have these server farm just trying to get this blockchain calculated. Anyways, that's kind of fun. I don't pretend to be an expert on it. I don't own any Bitcoin, but some people made a lot of money out of it. A lot of money. Okay, so we got parts of a computer, and just look at those, and each of those is mentioned there. Some of the things that we have. No, geez, maybe I need to bring this down a bit. So parts of a computer. Oh, then I won't see. All right, so we got power supply. Now the power supply is taking from the mains. These power supplies will work on 110 or 220. We're at 220, right? So I mean, you know, they got a transformer in them. They can take the power and change it from whatever's in the wall to what you've got. And so around the world, we do have different levels of power supply and different AC frequency. So like here, I think it's 60 hertz, in some places at 50. And here we got 220. But I mean, it ranges from 220 to 210, 220. United States is 110. Anyways, your computer probably will plug into both of those and handle it all right. And what it will do is it'll then take that 210 and it'll drop it down to 5 volts. So 5 volts is what's going to be powering most of this stuff here. So 5 volts will be powered to the motherboard, and these other devices will get their power from the motherboard. And so you see the motherboard there. In the middle, we've got the thing which seems to be most obvious, and that'll be the CPU. So CPU is going to be a chip which does the processing. Actually, CPU's got a lot of circuits in it. There's a lot of stuff going on in the CPU. Remember the von Neumann architecture? Oh, we got a video on the Harvard architecture, which you should look at some point too. So the CPU there, why does the CPU have a fan? Because it produces so much heat. And if it overheats, it will stop functioning. And so we've got a fan to draw the heat out of that. You got another fan here to draw the heat out of the power supply. And, you know, you could have other fans on it as well. So we've got some slots where we can add things. So we got some slots over here. I think that's for memory. We've got some add-on slots here. Now those slots are connected by a bus, different buses that connect through to the CPU. So we have our random access memory. It's going to be chips on a card. And then we plug those into the bus. And then the CPU is able to access that random access memory for its processing. Yeah, okay, so a VGA card is going to drive the screen. All right, and usually you're going to have some other thing going on. What? Don't see it. You know, you're going to have some kind of a, especially if you're playing games, VGA card might not be fast enough for you. So you have some kind of special graphics processor. And the graphics processor might be on a special card, or it might even be built into the motherboard. So when I say built into the motherboard, these things are sort of actually attached by pins that could be soldered on to it. Okay, so yeah, that's VGA card's going to give you video, and yeah, so this one here has got a fan on it, so that's probably got that's going to have a processor under there just for processing our video. Sound card. Yeah, we got, okay, so nowadays, the hard disk, nowadays, a lot of hard disks are being replaced by, we call it SSD, solid state drive. So solid state drive is just going to be a bunch of transistors that'll store data, and you won't have any moving parts. And there's advantages and disadvantages of that, but the big advantage is going to be a lot faster than a proper hard drive, which is the old style hard drive, which is a disk spinning and being read from a platter. So we don't have to do that with a SSD. All in one. So maybe you've got lots of slots, so you can stick in the little cards from your phone or your camera. Probably your phone is your camera. And yeah, we got some inputs and outputs things. All right, do I need to, okay, can I, no. The only way I'm going to see that stuff is if I make this, if I screen this up. I'm not liking this much. Oh, there we go. So again, these notes will all be there. There's some stuff there about the power supply, main board, motherboard, all of that stuff I think I've sort of mentioned, but you might want to go over those notes and look at them in your time later. It's just so you're ready for the quiz, all right? Just so that you have. Now here's the stuff about binary. Binary means 2. We only have 2 numbers that we work with, and we build up from there. So we have a 1 or a 0. 1 or 0 is a bit. So a bit is just one of those 2. And you can combine those bits to get more states. So as it says, if you're only working with 1 and 0, you can just have 2 states, on or off. If you put 2 bits together, then you can have 4 states, right? You can have 0, 0, 0, 1, 1, 0, and 1, 1. So there's our 4 states. So 0, 0, we can actually make numbers out of those, or you can make other things, but we use binary to make up numbers. So if we were to convert these to decimal numbers, we'd say this is 0, this is 1, this is 3, and this is 2. So we do 1, 0 before 1, 1, just like we do in decimal. What else we got there? All right, so what if you had, oh yeah, you can tell the number of states by raising to the power how many you've put together, how many 1s and 0s. So if you got 2 1s and 0s, one beside each other, that's 2 to the 2, which is 4 states. If you got 3 1s and 0s put beside each other, then that's going to be 2 to the 3, which is going to be 8 states. And if you have 4 bits, 0, 0, 0, 1, and etc. Then you could have 16 states. 2 to the 4 would be 16, right? So if you're going up, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32, etc. What else we got in there? Anything? I think that's it. Right. So I told you these wouldn't be very long. Is that? Oh, we got 12. We got 12 slides, not 8. So then we get to talk about computer programs. What does computer program do? Occupies, we use the RAM. RAM stands for random access memory. That's memory that can be addressed and accessed quickly from the CPU through the bus. It's got each cell can be addressed. It has an address that can access it. Yeah, and the address is now we talked about fetch, decode, and execute before, right? So fetch is going to be getting something from the memory. Could be an instruction. And then decode is going to be making sense of that instruction, translating, if you want to call it that, the instruction to know what it's supposed to do. And then execute is to actually do whatever that instruction is going to do. So every time we have a cycle in the clock, we have a clock on our computer. Every time we have a cycle on the clock, we do a number of those steps. Now, in some computer architectures, we do 2 out of 4 steps, and in some we do them all. But so you could say that at the very least, so if you've got a computer clock that's going at 2.3 gigahertz, that's billions of cycles per second. Then at the very slowest, you can do a billion executions of a program statement in that time. So here's something interesting. We've got 2 different architectures. At the top, we've got the Von Neumann architecture. Below it, oh, by the way, Von Neumann architecture, I call it Von Neumann architecture because the name is a German name. When I was looking at these things, the guy actually wasn't German. He's Hungarian, but his family, so there was I guess it was the Austro-Hungarian Empire, might have been a sort of a lag on from this, but anyways, his family were kind of important rich people, and he became part of the aristocracy. So it's sort of kind of like being a sheikh or something. But as a result of that, he came across a lot of money, and they gave him a new name, which sort of sounded German, Van Neumann. And that's how the Germans say it. But you'll hear a lot of people call him Van Neumann, and that's anglicizing it. I mean, because when an English speaking person looks at that word, they're going to say that's Neumann, but Germans say Neumann. I don't know about Hungarians, but anyways, I think he liked to be called Van Neumann, von Neumann. Anyway, so the architecture at the bottom is the Harvard architecture, which was designed after the von Neumann. It has some advantages and disadvantages, I guess you could say. Maybe one thing that you could notice about it is that we have, well, I know this one shows the data memory here, but actually what's happening is your memory can be used for both things. And notice we're using just a single bus to do everything. Whereas here we've, well, sorry, yeah, it actually, when I say a single bus, we got a single data bus that works with two different memory locations. Whereas, and actually those memory locations are not that separate in the Van Neumann architecture. But in the Harvard architecture, we've separated the memory locations quite differently. And so they're accessed by different buses. So maybe you can see here, we just got the one data bus for each of these three different activities. Whereas here we've got twice as many data buses for those three different activities. And so because of that, the Harvard architecture is a bit faster, okay? And so it can be used for things that need to go faster with smaller sort of purpose-built sort of systems. It does mention in your notes that it's used for small smartphones, and whereas the Van Neumann architecture was used for PCs mostly. So when we say smartphones, we would also include in that a lot of purpose-built sort of processors, I guess for like the CPU in your car, that type of thing. And so there's a few notes on that, just in case I forget to mention it. Yeah, but Harvard is faster. Van Neumann is more flexible. And yeah, so there's that. So this slide is referring to this cycle, the fetch, decode, execute cycle. And the fact that that fetch, execute, decode cycle happens, we can isolate the parts of the computer processor where those things happen. So the computer processor is actually got different components within it. And one of those is called a control unit. One of those is called the arithmetic logic unit. And we have registers. Now, registers in the CPU, they're just special memory. So they're kind of just like the memory in the random access memory. The difference only being is that they're actually inside the CPU so that they can be accessed a lot faster. And so the fetch, decode, execute cycle is represented here by those arrows. So that's our cycle going around there, right? Now the main memory here, that would be outside of the CPU. So all of this blue stuff and green stuff is actually inside the CPU. Outside the CPU is main memory. And actually, you know, it talks about the registers there. That's one form of memory. Actually, in the CPU, we got another couple of things. We got caches. We got L1 and L2 caches, which, yeah, they're not actually part of the main memory, but we got lots of memory in lots of different places on our computer, right? So what's first happening is we fetch an instruction. That's why this arrow is coming up from the main memory. The program will be loaded into the memory, and then the CPU has to fetch an instruction. That is done by we see there the control unit. Then we have to decode the instruction. All right. So that would be our second part of the cycle, where that's being decoded. And then we're going to pass that decoded instruction over to the ALU, which actually does the mathematics or other crunching that has to happen. So that's the execution. And so that when the instruction comes over there, it'll also have to get the data from wherever the data is stored. That data, it looks like it's coming from this way. So that means it's going to come across with the instruction, perhaps through the registers. And then lastly, it's going to execute the instruction. After it finishes executing the instruction, it will output the results to the main memory. And so that also is explained there in those notes. And there's even a video there that you could watch to help explain it. So, you know, just copy that. And when I say copy that, that's going to be on your D2L page, right? All of this is on your D2L page. You could sort of, so there's that video there. You can just click on it, I guess. And yeah, the idea here of the power, what are they Power Rangers, right? The idea being that something like that, I don't know. Yeah, something like that. They come in different colors, right? They look like they're riding motorcycles to me, but yeah. The idea being that, what is that happening? It looks like, it looks to us, what we see is something like this, right? We just see a computer which is just doing a lot of stuff really fast. But what we really need to understand is there's a lot of things happening, right? It's not just one thing happening. It's all these things come together, and that's what happens. And that's in our fetch, decode, execute cycle. All right, so here we have, can we make some kind of analogy that would be the fetch decode cycle, which is something that everybody, even people that don't do computers, would understand. And that might be cooking something. So we go and we get a cookbook and we look at some instructions. That would be a fetch. So the cookbook would be like some memory, I guess. And then we, as the person, so we could say that the CPU has sort of brain-like characters, you know. People sometimes refer to the CPU as the brain of the computer. That's what I mean. That's where those kind of, what we would call thinking, the closest thing that a computer does to it, is happening in the CPU. So in the CPU, we would try and understand that instruction. For us, we do that in our head, right? Once we've read the instructions from the cookbook, we try and understand it. And that would be decoding. That's the decode part of the cycle. And we would go and get the ingredients we need from the store, because I don't know if you remember, in that part of the cycle, we got the data. And so once we've done that, then we go ahead and start doing stuff. That's the execute. And that's probably a good place to stop for a minute. And then I'll restart the Zoom meeting in a couple minutes. It'll take me a couple minutes to do that. So maybe you guys like to take a break. The next lecture is shorter. So I got 2 lectures today. The next one's shorter. Is that all right? Okay, go for it. So I'm going to stop this and that will record. So who we got there? We got Hassan, Sahar, and Zahra. Okay, I guess they're quarantined.